Rahul, would you like to say how you are doing? If you have any specific issues, questions.
Yes, sir. Good evening.
Good
So I have
evening.
performed the four tasks you have given, and for my project, the thermal conductivity one, I'm performing the model training. So I performed like KNN, a random forest decision tree, and yeah, that would be. I'll have to validate it. Then I'll send it the results.
Yes, of course, I understand. So, when you one of the have you tried any of the tasks that I either listed on my slides or whatever I sent last time over email?
Yeah, I performed all the tasks, the four tasks you have given, the four assignments.
Uh-huh. Okay, so just tell me, can you show me your code, the random forest one?
Oh, then I have to join with another device. So I've sent you the request.
No, I don't have any control over it. So you are joining through WebEx, right?
Yeah, I have two devices. So with the another device, I have performed all the tasks and I'm joining.
I
Um,
see. Uh, is it possible to transfer your files to this computer and then show
okay.
it? Do you need a permission to share your screen?
Uh, I have to check.
I don't think so. Maybe not. Just try. Is it possible for you to share the screen?
Yes,
Yeah, I can see your screen. Now you can focus on
but I
your.
have to transfer it here. So is it possible to join with another device here? So I can see.
See, I don't have any control over this thing. These are controlled from the HBNI office, so you can try it out. I don't. If you are joining through your browser, right?
Yeah.
So I don't think there is anything specific to a particular machine. You should be able to join it. Join from another machine.
Okay. Okay.
Yes. I can see your screen.
Yeah. So the code you have shared, I just modified it for the different data set you have asked us to do.
Mm-hmm.
So this is for the first assignment.
So what are we? What are you showing here? Scatter plot for which one?
For first assignment, the data set you have provided for to optimize the random forest hyperparameters. So this
Mm.
is for the test set, the prediction
Mm.
of test set, the scatter plot, what is the prediction and
So can you show me what the optimized hyperparameters are?
yeah, here the CCP alpha is 0.0, the max depth is 20.
Can you show me the code that I sent? Yeah. No, where the cross validation is done.
Yeah, yeah.
Right. So the depth is 2 to 20. In fact, I had specifically, not in my email, but in the class, I had said, see, if you look at that parameter depth, right?
Yeah.
Depth is, yes, the line above that. Just
Ah,
highlight on that line. Yes. So depth is now between 2 and 20. And I had mentioned the same thing in the last class. So when I optimize it through grid search, I get a value of 20. So maybe my range is not correct because I get a value which is at the limit. So I
hmm.
had in fact suggested that you should extend this range and try to see if you get a better value,
Okay.
a different value than 20.
We can also set it none to none. So
Set it to what?
none. I mean, it can go the further it possible. So,
Yeah, whatever, but that optimization needs to be done properly because
yeah.
this may not be the correct value. It may be the correct value, it may not be the correct value, or
Hmm.
correct in the sense optimal value.
Yeah.
Did you try optimizing any of the other hyperparameters which are not listed in this list, parameters list here, but are there on the scikit-learn
Uh, Not
page?
in this assignment. I can perform it with other hyperparameters, but
Mm,
I've not performed
mm,
in this.
mm.
They are bootstrap on all the stuff, so I can.
No, no, just using, I mean, not bootstrapping it is in any way it is doing bootstrapping.
Aha.
Yeah, and did you use it for the band gap? This
Aha.
is for the formation energy, right?
It's a
ABAC3.
formation ratio.
Did you try it for the band gap?
Yeah. I just use the same code but change the CSV files and the names of the save files.
So can I see your results for this?
Yeah, these are very bad.
These are very bad, right? And did you create the bigger data set for band gap that I had suggested?
From materials project.
Yes.
Yeah, yeah. So there are two things you have asked us to do. One is to consider the eigenvalues of the sign matrix, and other one is to consider the independent elements.
Hmm.
Yeah, these are also very bad after performing the model.
So this is for the bigger data set, is it?
This was the bigger data set with considering the independent parameters.
Hmm. Yeah, not surprising. Um, and did if you use independent elements of the sign matrix versus if you use the eigenvalues only, is there a difference?
Uh, not that much.
Seems to be rather flat. Um, okay. Yeah. So I have in these sort of tasks, I asked you to use sign matrix or the eigenvalues of sign matrix because one of the reasons is that the size of that is the feature set size would be small. If you try to use a CSA for MBTR, for example, the feature space dimension would be very large, and that requires careful handling. And if you have a small data set, that creates problem. That is why I have. It's only partly because of computational reasons and partly because the data sets are not very large that I have mostly asked you to work with the sign matrix features. But I hope that in your project you are not confined to sign matrix alone. Um,
No, no, no. I'm considering both the sign matrix and atom-centered symmetry function.
no, there is nothing special about sign matrix. Again, let me emphasize that in this, in these sort of hands-on examples, I'm asking you to work with the sign matrix simply because it's a small feature space. It's easier to handle computationally. It will be quick. So that is the only reason I asked you to work with sign matrix. If you want correct or better results, better predictions for many of the physical quantities, sign matrix alone won't be very good. I is my intuition and understanding. Uh, okay. Let us see if Shulagna has any questions or anything. Shulagna, have you tried doing any of these? Can you please
Uh,
unmute your?
y- yes, sir. We have tried doing the assignments given by you.
Hmm. And can you, yeah, can you please show me what you tried, what you got?
Sir, I am trying to log in, but uh, I don't know. It's not opening. Like,
You mean sharing?
yes, sir. I'm trying to join from another device.
Uh-huh.
So, but maybe the internet speed is low, so it is taking time.
Okay.
Sir, up to what we have done is we have downloaded the data set. Um, so for the third part, that is the download of data set for band gaps in between 0.2 to 1 electron volt with number of elements less than 20. So we have tried to download the data set, and that has happened.
Mm,
And regarding the previous two problems, said that part the optimize the hyper parameters in the RF regressor for prediction. Said that part has been done by my teammate Shubhankarta. So I have come to SINP to understand his like in which way he has solved the problem.
mhm.
So Yes.
Yeah, actually, yeah, understanding in the sense we have discussed this more than once in the class. It is sort of automatically done via Greek search and cross validation by scikit-learn. So, if you have understood cross validation and greed search is a very simple concept, but if you have understood cross validation, then you understand how it has been done. So, have you followed up on that, the cross validation?
Yes, sir. I am trying to understand your code, and also actually we have tried to modify or simplify the code a little bit. So in that part we have tried.
Mhm. Yeah, the code I shared may not be the optimally written one. It was something that was done quickly. Uh, yeah, but I'm specifically asking about the not my code. I'm asking about, are you clear about the concept of cross validation?
Yes, sir. The cross validation means the difference between the predicted value and the calculated value. Uh, so is it
No,
like that?
no, no, no. It isn't. That is your error. That is your prediction error. You can take the absolute value of the difference. That's your absolute deviation. And if you take the average of all such deviations for the test set, you get mean absolute error. So that is how you firstly you may be optimizing, that is minimizing that quantity to fit the model, to train the model parameters. And after you have trained your model, you could be applying the model to the test set and measuring this mean absolute error, which is a measure of performance of the model on a the test data set. But that is not cross validation. Rahul, would you like to, are you clear about cross validation, and can you explain what it is? Can you hear me, Rahul? Okay, let me see if I can open my slides once more, and I'll just, maybe one last time, I'll explain what cross validation is. You have it in one of my earlier lectures also. Can you see my screen? Shulagna, can you see my screen?
Yes, sir.
All right. So just focus on the last bit, this figure at the bottom right. Uh,
Yes, sir.
so, so I explained this in the context of the linear model with shrinkage, lasso or ridge regression. But this idea of cross validation is the same no matter what or how many hyperparameters you have in your model. So here is your, this sort of orange part is your entire data set, right? And you have first split it into training set and the test set. Now you
Yes, sir.
take your training set, and suppose I'm doing 5-fold cross validation. How many folds you split it into? I mean, there is no sort of recipe for that. If you have a lot of data, you can do a 10-fold cross validation. If you don't have that much, you can do 5 is sort of a reasonable number. So you basically make roughly 5 equal parts of that data, and each one of those is called a fold. So you split your data into 5 folds. Now step 1, you train your model on fold 1, fold 2, 3, 4 and 5. So all the data from fold 2 to fold 5, you train your model. Then you test it out on fold 1. Test meaning whatever loss function you are trying to optimize. It could be the mean absolute error. So you get a score, right? You get a mean absolute error, which is mean absolute error 1. Now you come to the second step, the second line here. You train your data, train your model combining data in fold 1, fold 3, fold 4, fold 5. Fold 2 is not used. And you test your model on fold 2. So you get another score for mean absolute error, which is MAC or mean squared error, whatever you are using. MAC2, let's say. Similarly, when you come to the third line, you hold out fold 3, you train your model on the other 4 folds of data, and you test it out on fold 3, you get a score. You get a new score, new MAC3, and so on. So if you are doing 5-fold cross validation, you get 5 such MAC scores. And then you take an average of that, of all those. So your final cross validation score for a k-fold cross validation, and in this picture it is a 5-fold cross validation, is just the average over all these errors. Okay, that's your cross validation score. Now you have, in this case, you have one parameter to optimize alpha. So you can take a certain set of values of alpha, and you do this, you calculate this CV, the cross validation score, at each value of lambda. So at each value of lambda, you are calculating 5 different mean squared errors and taking their average, then finally taking their average. So at each alpha, you get a cross validation score, and you ask what is the value of alpha at which the cross validation score is the minimum, because you're trying to minimize mean squared error. So that value of alpha is the optimal value. Now suppose, now this is just one parameter. Now suppose you have a model like the random forest which has many parameters. So what do you do? Think of these parameters as making up a space, and along each axis you make a grid. Okay, so if there are n number of hyperparameters, and you are making n1 divisions along the first one, n2 divisions along the second one, you get n1 times n2 times whatever, those many grid points, right? So you do this, you calculate the cross validation score at each one of these grid points in the hyperparameter space. Whichever point in the hyperparameter space gives you the minimum cross validation score is your optimum set of hyperparameters. This is a method called, this is called grid search, because you are just making a grid in the hyperparameter space. At each grid point you are calculating the cross validation score, and then you are comparing them to see which one gives you the lowest value, and that's the, then you choose that set of hyperparameter values to train the model. So this whole business is about hyperparameter optimization. Once the hyperparameters have been optimized, then you use this full training data here, the green part, to train your model. At that step, hyperparameters are fixed. You are only fitting the model parameters. In the linear model, that means in that step you will be fitting this coefficients W using the entire training data, and alpha will be fixed. So is that clear? There are two steps. One is the hyperparameter optimization, and then there is this model training, that is fixing the parameters, fitting the parameters, keeping the hyperparameters fixed to their optimal set of values. So that is what is called cross validation. Okay. So yeah, I hope it is clearer. Uh, that is what we were doing. But what I would like you to do, and I will share it over email, is that you should try to optimize the other parameters also, which we have. I did not mention in that. I did not do in the script that I shared with you. Is there anything else that you would like to discuss? Anything related to your project? Sulagna, if you have any questions, you can ask me because I don't want to do anything new today.
Yes, sir. Sir, as it was discussed in the past tutorial that we may need to change the topic of the project because not we were not be able to find many compounds with transition metal ion doping for our band gap prediction. So, sir,
Mhm.
then maybe since we are working with this uh, this project, I mean this notebook now, maybe we can change our project accordingly. Uh,
Sorry, say that again.
said since we are now doing this assignment like that you gave on pancake prediction, said
Mhm.
we can now also modify our project work according to this or something similar to this because it is not possible for us to find many transition metal ion doped compounds that we proposed earlier. Um,
Right. Uh, yeah, exactly. You won't find data and generating data, then fitting your model. That will be too much of work. It is not worth the effort for project in a course like this. Okay, that requires a lot of computation. So if you want to stick to band gap prediction, yes. So one thing possibly you can do is you can I mean, you can select different classes of materials from materials project. Let's say I'm just giving you suggestion, okay?
okay,
And
sir.
different classes of materials, and then you could try to see which um, features and which model gives you the best results in what class of materials for band gap prediction. All right. Um, is that clear?
Yes, sir, that is clear. Sir, different by different classes, does that mean like perovskite materials or Hazler alloys, like that?
Yes, yes, yes. You can perovskites can be one class of materials, and then let's say transition metal oxides can be another class of materials, or generally transition metal oxides, chalcogenides. These could be one class of materials.
Okay, sir. Okay, sir. Then we will try to prepare the database accordingly. And sir, one more thing that the deadline for our midterm submission has already passed, but our target for that was to at least prepare the data set. Sir, so
Mhm.
if we are able to create the data set successfully, then can we submit it? Like,
Yes,
uh,
you submit it. I will circulate a mail. So today is what, the 17th. So let's say another week's time. Uh, you will give you another week to submit your midterm report.
okay,
So
sir. Thank you, sir.
okay, all right. So we'll do that. And in fact, in the next lecture, I want to at least definitely by this week. So far we have been talking about different features which you need to create. What we have not talked about, what I have not talked about is one way of pictorially representing material. So that is something I would like to cover either in the next lecture or by Friday, definitely. And that may be a very convenient way of that is maybe a convenient representation, particularly for neural networks. So next class I will discuss neural networks for property prediction, and then that is another thing you may consider for any model that you train. I mean, your problem remains the same, but this can be an additional feature or additional type of materials representation which you can test out.
Okay, sir. Sir, then first we would like to complete or try with the perovskite material or transition metal oxides that you have suggested based on the assignments that you have given earlier.
Mhm.
Then after that we can then modify accordingly before the final submission.
Yes, so I would suggest that you go this way. First you focus on a particular class of materials. Okay, let's see whether you get a larger data set for transition metal oxides and chalcogenides, or whether there is a larger set for perovskite materials. Whichever you get, you stick to that, and then given that data set, you try different features and different types of models that we have discussed,
Okay, sir.
and you note their performance.
Okay, sir.
All right.
Okay, sir. Okay, sir. And we will communicate with you our results. Like from
Sure.
now on, we will try to maintain a chain of emails and results with you.
Yes. Okay. That's fine.
Okay, sir.
So that's all right today. Then we'll close it early today, and we'll take it up next time. That is Wednesday.
Okay, sir. Thank you, sir.
Okay.